Hi again. All right, so to recap, we had just finished talking about a new property of a system that I called entropy. I said that entropy is a property that is a state of a system, the way temperature is a state of a system, the way the volume, the pressure, the mass are all state variables for the system. So the idea is that entropy is just another thing that we can use to help characterize what our system looks like. And I used the example of a glass of water that in one case is liquid, in other case is frozen, or in its liquid phase and its solid phase. And I said that we can think of the ordering of the water molecules in the liquid phase is highly random. And so there's uncountable numbers of possible arrangements of the water molecules, whereas in their frozen state, they take up approximately, and I'll talk about that approximately qualification a little bit later. But anyway, they take approximately a crystalline arrangement with an approximately fixed arrangement, and so that the number of possible arrangements of these water molecules in the solid state is very small. It's more than one, but it's very small anyway. And so in that sense, this is a less random system, a less disordered system than the same water molecules in the liquid state. And so entropy then is a concept that has been designed to describe this difference in the ordering, the randomness of a system. The symbol given to entropy is capital S, and I don't know this for sure, but I think that it's given the symbol S because we weren't using S for anything else relevant in thermodynamics. And so S very generally is, or very approximately, I should say, is defined as the sum over the number of particles that you have in your system, which you can imagine can be absolutely huge. The change in energy of the ith particle divided by the temperature of the system. Okay, and so what happens is, or I should say, I'm sorry, 1 second here. Yeah. So if your system is at some temperature, if you have some heat that goes into or out of the system, then the system becomes more or less random. If you add heat to the system, that means that the particles gain kinetic energy. Okay, and generally that should mean that the temperature increases, but it gets a little more complicated than that. I don't want to go into it deeply, but you can increase the kinetic energy by adding heat without changing the temperature, and what you actually end up doing is changing the entropy of the system, making it more random without increasing the temperature. It's a little complicated, the relationship between entropy and temperature, and I don't want to go into it too deeply here. I just want to get across the idea of entropy. Notice that the units here are joules per Kelvin, and I think at this point I have not yet recorded a lecture on what the Kelvin is. So I'm going to say to you that, and this is weird timing, because from where I stand, and from the moment in time when I'm recording this lecture, I haven't done the recording on the Kelvin temperature scale yet. But now that I've realized that, after I finish this recording, I'm going to record that lecture, and then I'll put it in front of this one. And so from your point of view, I have already recorded that lecture. Isn't that weird? Don't you love that? So in any case, I'm going to assume that you know what the Kelvin is. It's the, so it's the absolute SI unit of temperature. on the absolute scale. Okay, so anyway, so the units of entropy then are joules per Kelvin for whatever that's worth. But that's right. The main thing I want to get across here, I'm not even going to bother calculating anything. I just want to give you a qualitative idea of the second law of thermodynamics. The other thing that can happen, the other way entropy can change is if heat flows out of the system. Now, if heat flows out, then, so delta Q is actually negative, right? Then the entropy decreases. The system becomes less random, okay? And so that's fine. The second, now for the second law of thermodynamics. Let's assume, let's go back to our frozen glass of water here. Okay. Actually, let's start with our liquid glass here. What I'm going to do with my liquid glass, actually, I think I'm just going to redraw it over here. So my liquid glass of water. Highly disordered, high randomness, high entropy. Okay. Now, I've mentioned that the temperature of this thing, and for that matter, the randomness, the entropy is affected and determined by how much kinetic energy these particles have. What I'm going to do is now pack my glass of water here in styrofoam. That's supposed to be styrofoam there. The purpose of all this is to isolate my glass of water in a thermal sense. In other words, that whatever temperature the glass of water is at, it's going to stay there. I'm not, the styrofoam surrounding this thing is going to prevent any heat from getting in to the glass, so the temperature of the water can't increase, and that, for that matter, the whatever heat, whatever energy there is in the water can never leave either. So we've thermally isolated the system, as we say. Okay. And that way, I just don't. In other words, I have a thermally closed system. Okay. In fact, if you remember a few lectures ago, I defined three names for our system, or three states of our system: an open system, a closed system, and an isolated system. So this system, so closed, remember, was that mass could not enter or leave, but heat could. But no, this is going to be an isolated system. So not only mass cannot leave, but neither can the mass cannot change, but neither can the energy content, neither can the temperature. So this is an isolated system. All right. As such, we can then ask, okay, if we leave that there, if we leave that glass of water there over time, what will happen to it in a temperature sense, in a thermal sense, in a thermodynamic sense? And your first instinct might be, your first instinct might be to say, well, nothing will happen to it. It'll sit there, it'll stay the same temperature. Why? Because we isolated it so that it would. Okay, so it'll never change temperature. It'll just sit there. It'll continue to be a glass of water until you open your open your styrofoam box back up and look at it. And it turns out that's exactly correct. Your instinct is exactly true. But it's not obvious, if you think about it, that that should be the case. Because after all, the temperature of this thing, as I say, is a measure of its kinetic energy, okay? And what if, just by chance, well, how could it gain or lose energy? Well, the way it could lose energy, well, the way it could gain energy is, what if the sides of the styrofoam, which are after all just made of particles themselves that are at some temperature, what if the styrofoam molecules collide with the surface of the glass, and the surface of the glass in turn collides with the water molecules? In short, there's an energy transfer between the styrofoam, the glass, the water, and the energy, could flow from styrofoam to glass to water, but it could happen the other way as well. The water, a particular water molecule could collide with the glass, and in that single collision, the water molecule could lose kinetic energy, give that kinetic energy up to the glass. The glass molecule in turn collides with a styrofoam molecule, and the glass molecule also gives up its kinetic energy to the styrofoam. And the result of that is that overall, on balance, the water would get colder, the glass would get colder, and the styrofoam would get hotter. Okay? And what if, instead of just one water molecule doing what I just described, and then the glass molecules doing what I just described, what if all of them did that all at once? And that seems at least possible, because after all, these water molecules are moving randomly. And it's not likely to happen, perhaps, but what if out of the course of gazillions of possible arrangements, one of them involved the water molecules all simultaneously losing energy to the glass, to the styrofoam, okay? In which case, the temperature of the glass would drop, the entropy of the system would also decrease because it would become more random, okay? You think, well, the temperature drops, so the entropy would increase, but no, the temperature would stay the same, but the heat would flow out. And so there would be a loss of heat to the system, so the entropy would decrease, okay, if all of that happened. Well, that sounds nice if improbable, but it is improbable. It is improbable, and in fact, for reasons that are too complicated to go into, because they're highly mathematical, and I don't want to bore you to death with the mathematics. Suffice to say that if you think about all of the possible arrangements that these water molecules could have, there's one of them, or maybe two of them, that would result in them losing energy, and therefore losing entropy, having the entropy decrease. Out of the uncountable number of possible arrangements, 7 of them would represent the temperature decreasing. And so on the face of it, it seems maybe possible, but so improbable that it's not even worth talking about. Well, that's exactly correct. But in fact, it gets stronger than that. It turns out that the probability of this happening is exactly 0. At least that's what the second law of thermodynamics tells us. Okay. That's the second law of thermodynamics. The entropy of an isolated system never does decrease. Okay? It can increase easily. It can stay the same easily, but it cannot decrease. It just does not happen. Okay? Up to now, at the time of this recording, the second law of thermodynamics is not quite on the same footing as the law of conservation of energy, or even the first law of thermodynamics, or conservation of momentum, or anything like that. It is more of a probabilistic statistical matter. But I was actually just reading a paper a couple of months ago as I record this, in May of 2017, that the second law has been actually put down on a firm theoretical basis. that elevates it to the same level of certainty as the law of conservation of energy or conservation of charge or conservation of angular momentum, all the rest of the conservation principles. So this, you can take the second law of thermodynamics as a fundamental law of nature, okay? Basically what it says is the randomness, the disorder, the entropy of a system just never decreases. If a system is random, there's a good reason for it, and it will stay random, and it won't decrease spontaneously. Okay? Which leads to some interesting thought experiments that will turn out can't happen, and we're glad of them. And I'll describe a few of those, and we'll do some sample calculations in the next recording.